Okay, welcome back. Happy Monday. Today, quiz number 5 is due. Go ahead and throw it in the folder for me right now, and I'll grade it and get it back to you. This quiz was pretty much all about the series tests, as you saw, and it is, again, a very low, it's not worth a lot in terms of your final grade. What's it called? Low stakes. It's a low stakes thing where I can give you feedback about writing all these nice proofs that we've been working on. So project 8 is now assigned. Go ahead and grab one from your table. It is all about power series. We will cover that material today. Any questions on the calendar? Okay. All right, so let's get started here on page 41. I'm actually going to jump a tiny bit to the next page. We're going to jump to 42. We're just going to dive right in. I want to skip some stuff in the demo to give you more time to practice in the activity. Let's see how this goes. So this thing right here is called a power series. X minus 2 minus x minus 2 squared over 4 plus x minus 2 cubed over 9 minus etc. So here's what it means. Suppose, for example, that x is equal to 3. Just picking a number. What's the first thing in the parentheses? 1 minus, what's next? 1/4 plus, when x is 3, 1/9 minus 1/16 plus dot dot dot, yeah? What series test could we use to determine if that series converges or diverges? We could use the alternating series test, right? The terms, if we ignore the alternating piece, are the terms decreasing and going to 0? Yeah, so that series right there converges. That means that this original series converges when x equals 3, yes? Okay, let's pick another value for x. Suppose that I pick x equals, oh, I don't know, 10. X equals 10. I'm just making up a number and I'm not confident that that's a good number to make up, so I'm just going to scratch that. I'm going to say x equals 3, we've already decided the series converges. Perhaps other values of x, the series will also converge, but maybe for some values of x, the series will diverge. Fair? So what we're really doing here is looking at an infinite polynomial where for some values of x, the series converges, and for other values, the series diverges. And our goal is to determine which values of x are which. We want to find all of the x's for which that series converges, and therefore by process of elimination also all values of x for which the series diverges. So there is a standard technique for doing this kind of problem. First step, you'll see why we need to do this. But we got to first write this series in closed form, meaning in sigma notation. So let's begin there. First thing I see is that every single one of these has x minus 2 to a power. So how about we do x minus 2 to the n? Okay. Next thing I see is a division. And I have to recognize what special numbers are on the bottom. 4, 9, 16. Those are the perfect squares. So the question is it like n squared? Sometimes it's like n plus 1 squared. It could be off a little bit, so we just have to check. Is that the right relationship there? 3 squared is 9, 4 squared is 16. Okay, so it feels like it's just n squared. All right, so we got lucky there, n squared. It's the only other piece we need to deal with. Yeah, we do have to deal with that part, but we also have to deal with the alternating sign, right? And so -1 to the something. I'm going to put n, and it seems like roughly half the time that's right, and the other half the time we have to make it n plus 1. Okay, so we'll figure out which one it is in just a second. Last piece here is starting value and ending value. N equals what? N is the power. What's the starting value? 1. Again, like half the time it's 1, and maybe half the time it's 0. You just have to look at it and see. And this goes forever, so it's infinity. So the only other piece was this, is -1 to the n. Is that the right power up there? Well, if n is equal to 1, is it a positive or a negative? That's negative. Do I want that first term to be negative? Nope. So make it a plus 1. Because now when n is 1, how much is the power? 2. And negative 1 squared is the positive 1. That's the first term. That's what I want. Okay, so this guy's in closed form. Yeah, you could do n minus 1. Yeah, you just have to jog it. Yeah, and that's fine. Yeah, n plus 1 or n minus 1 is okay. Okay, so again, we had said we were going to try to figure out the set of all the x's for which that series converges. Now, I know it looks a little bit more intimidating than the series we've been playing with the last few weeks because it has x in it, but n is still the thing to focus on. And what I see here is x minus 2, that's just some number in my mind, raised to the n. That is an exponential piece, like 2 to the n or 5 to the n. And there was a standard test we would use when we saw exponential pieces, and that was the ratio test. Remember? Ratio test was good for factorials and for exponential things, a number to the n. That's what I have. And so we're going to use the ratio test. And using the ratio test is the standard way to handle power series. You're going to do it a bunch in the activity, and you're going to do it 5 times on the project I just handed out. So if you recall, the ratio test says take a limit as n goes to infinity of the absolute value. And it's a big old fraction. Yeah, where does the original go? Top or bottom? Original goes on the bottom. So we just copy it as is downstairs. And then remember to figure out what goes on top. All the n's become n plus 1. So that n becomes n plus 1. N plus 1 plus 1 is n plus 2. X minus 2 to the n plus 1. And then downstairs, I'm going to show you a common mistake. Don't put this. You're not adding 1 to like everything. You're replacing n with n plus 1. So it's n plus 1 quantity squared. Okay, now we've got a little bit of algebra to do before we get to take this limit, which means we have to copy the limit for a little while first. Limit n goes to infinity, absolute value. Okay, first of all, that negative 1 to the n plus 2 is either positive 1 or negative 1, but inside of the absolute value, it is positive 1. And so I'm not going to write either of those negative ones from here on out. I do have to write the top part here, x minus 2 to the n plus 1 over n plus 1 squared. And then we'll do our standard division becomes multiplication and then flip the bottom. So what do we have now upstairs? N squared over minus 2 to the n. Great. Okay, this one equals. All right, I have x minus 2 to the n plus 1, and I have x minus 2 to the n. Almost all of them cancel. What's left? X minus 2 on top. That's it, right? There's just one more of those on top. So still have to write the limit. I think this is the last time we have to write the limit. Note that we're still copying the absolute value. It's important here. Single x minus 2 on the top. And then I'm going to copy everything else. Okay, n is going to infinity. I see an n squared on the top. On the bottom, I see n squared plus some other things I don't care about, right? This is that, like I'm imagining distributing on the bottom, it's n squared plus lower order terms. The top is n squared, the bottom is n squared. These two things together, what are they approaching when n goes to infinity? 1, right? N squared, n squared. Which means the whole thing is approaching that x minus 2 times 1. Except there's an important detail that I had and then I lost. And that important detail is that absolute value. Stop. X could be negative, couldn't it? And so the absolute value might still play a role there. So that's why we needed to keep it the whole time. If x is -1, then that whole thing inside is -3, but you still have to take the absolute value and make it +3. Okay? And so our limit turned out to be 1. Keep in mind that the limit, for the limit, the variable is n. X is just a constant and it's just hanging out waiting for you to deal with the n pieces. Okay, there we go. That's the conclusion of the limit calculation. Remember, the ratio test says, hey, after you do that limit, the series will converge if that limit is less than what number? Ratio test. Less than 1. That's what the ratio test says. The series will converge if the limit is less than 1. So I say, hey, I'd really like to know where this thing converges, so I'm going to make that limit less than 1. So this piece right here is using the ratio test. It's always less than 1. That's what you want. Okay. So now we have to see if we remember some things about absolute value inequalities. In my mind, this right here is the absolute value of some number, and it's less than 1. Make up a number that you could put inside of here that would still be less than 1 when you do the absolute value. Negative point, how much? Negative 0.05. When you take the absolute value, is it less than 1? Yes, make up one more number. Anybody else? Yeah. 0.5. Absolute value is less than 1? Yes. Now let's make up a number that doesn't work. 10 is no good because the absolute value of 10 is not less than 1. 2 is no good because the absolute value of 2 is not less than 1. Make up a negative number that is no good. Negative 4 is no good because the absolute value is 4, which is not less than 1. So hopefully we convince ourselves that the only things that are allowed to be inside of that absolute value are numbers between -1 and 1. Buy it? Anything between -1 and 1 is good. Anything outside of that range is no good. And so this is our standard kind of thing, where you just take that 1 and you make it a 1 and a -1. And you put your stuff in between. Okay, so add 2 to all 3 pieces here. What do we get here? 1 less than x is less than 3. Yes? Okay, so what that means is that if you pick any x between 1 and 3, and you plug it into the original series, for all of these x's, you will get a series that converges. Any x you pick between 1 and 3, plug it in there, you'll get a series that converges using the ratio test. And that's kind of cool because we essentially just did infinitely many ratio tests all in one shot. Right? We just proved infinitely many series converge. Any number between 1 and 3, we just proved that that series right there converges. But we did infinitely many of them in just one big calculation. Okay. Likewise, if you pick a number bigger than x equals 3, like 4 or 100, and you plug it in, that series is going to diverge because that limit is not going to be less than 1. It's going to be greater than 1. If you pick x equals 4 or 5 or 6, the series will diverge. If you pick x equals 0 or -1 or -2, the series will diverge. There is a little bit more work we have to do, though. Remember, the ratio test said that if your limit is less than 1, converge. If your limit is greater than 1, diverge. If your limit equals 1, you can't use the ratio test. The ratio test is inconclusive. And there are two numbers that make this thing right here not less than 1, but equal to 1. What value of x can I put there to make this equal 1? You can put 3, or you can put 1. Yes? Which are always going to be the endpoints of whatever interval we come up with here. And so we need to do a completely separate test on the endpoints here. The ratio test simply will not work. It will give us that inconclusive limit of 1. So let's give it a shot. Also standard here, test the endpoints. Okay, x equals 3. All right, I don't have it on my page, but you have it at the top of your page. So we're plugging x equals 3 in for all of those x's. I accidentally picked x equals 3 when I first started playing with this one at the start of today's class, but let's pretend we didn't pick that one before and do it now. What do you get in the first parentheses when x is 3? 1 plus, minus, what's the next one? 1/4, and then plus, again, x equals 3 everywhere. So all those parentheses just become 1. Minus a ninth, plus a ninth, minus a 16th, plus dot, dot. And we decided up above, accidentally, that does that series converge or diverge? We said we were going to use the alternating series test, right? And we said the terms are decreasing and going to 0, and so the alternating series test told us, yeah, that series converges. So this thing here converges by the AST. I'm going to write here, we have not shown the details, but you will show the details in the activity and you'll show the details in the project. Let's try the other endpoint. X equals -1, x equals 1. If x equals 1, go all the way back to the top of the page. How much is in every parentheses? -1. So every parentheses is going to become a -1, okay? So the first term is -1. Minus, what's the next thing? -1/4, is that right? I don't think that's right. What should it be? Yeah, it's supposed to be -1 squared. I'm going to write it that way. Yes? Right. And then the next one is a plus, -1 to the third, divide by 9. We'll write one more, minus -1 to the 4 over 16. Yeah? Yeah, so I need to figure out what's really going on. There's just too many negatives and too many parentheses. So let's figure out what this thing is. -1, okay, sure, minus -1 squared. That's +1, but it's subtract, right? So that really is subtract a quarter. And then how about this next one? That's negative, and there's a plus sign, so it stays negative. And the next one? Yeah, that's also negative. Okay, I think I see the pattern here. Every single one of these turned out to be negative. Yeah? So can we figure out whether that series converges or diverges? Can we use the alternating series test again? It's not alternating anymore. Don't bother using the ratio test. You're going to get 1. That's how we ended up deciding to test these two numbers separately. Ratio test will definitely give you 1. It's a good try. It's not geometric, though. It's not the same multiplier to get from one term to the next. It does have a name, though. The series has a name. It does absolutely converge, yeah, but I need to know the name of this series. This is 1 over n squared, isn't it? Yes, 1 over n squared. And 1 over n squared has a name. It's close. P series. Yes, this is a P series. So this is really negative summation 1 over n squared. And you could maybe even see that without writing these terms out, like in fraction form. If you go back to the original, and if we said 16. 16. So way back up here, we decided that in this case, all of this stuff turned out to just be -1. So it's really a -1 over n squared, right? It's right there. And that's a P series. And does this P series converge or diverge? Converges because the P is greater than 1, right? So convergent P series. And again, if you start at -1 and you subtract smaller and smaller things, you are, but what if, just want to play here. So what if it was something like -1 minus a half minus a third? Something like that. We have -1 and we're subtracting smaller and smaller things. So this is the harmonic, isn't it? And we know that the harmonic is that really weird, like it feels like it should converge, but it diverges. Yeah. Okay, so at the two endpoints, x equals 3, turned out the series converged. X equals x equals 1, the series also converged. And so now I think we're ready to really write down a brand new phrase here. It is called, where is it? It's probably not on this page. Here we go. We're going to write down this thing called the interval of convergence. We'll abbreviate it IOC. It just means the set of all the x's for which that original series converges. So back where we are here, writing our final answer. The interval of convergence equals. Okay, so we said originally all the x's between 1 and 3. Did the thing converge at x equals 3? Yes. So now all of a sudden it's a less than or equal to 3. Did the thing converge at x equals 1? Yes, it did. So it's a less than or equal to 1. If you are an interval notation kind of person, then you can write it that way. And yeah, and so these series with x's in them can do kind of strange things in that this is one possibility where it converges at both endpoints. Other possibilities will involve diverging at both endpoints, but then there'll be the kind of mix and match ones where it converges on one side but diverges on the other, or converges on the first side and diverges on the second. It can do all 4 of those possibilities. So you really do have to test the endpoints completely separately. Okay? All right, so we skipped this definition here. We'll just read it real quick. A power series about x equals a is a polynomial with infinitely many terms, as illustrated here. So it's just a number plus a number times x minus a plus a number times x minus a squared plus etc. How much was a in the example that we just did? 2. Right? It was x minus 2 in all of them. And then we just had all these numbers and then all those powers. That's it. So I think it's called the power series because of the powers on the. What about x equals a? Yeah, it's a power series about we're just telling you what that number is. We're telling you the center of the series. What's the middle of this interval down here? What number is in the middle between the 1 and the 3? It's 2, right? 2 is right smack dab in the middle, and 2 is no coincidence. But 2 is that number. It's just part of the vocabulary here. We're just telling you the center of this thing is x equals 2. x equals a in general. Okay, so last piece here. It says that the interval of convergence is centered at A. This always happens at A equals 2 in our case. We call the distance from A to one of the endpoints the radius of convergence. Let's find that here. Radius of convergence. How far is it from the center to one of the ends? It is 1, right? From 2 to 3 or from 2 to 1. Radius of convergence is 1. That's all. It just tells you how far you get to go in either direction and still converge. Okay, so you are going to do 4 problems in the activity. For each of the 4 problems, you're going to do a big old ratio test, including the absolute value there. And then you're going to do the endpoint separately, which is like 2 completely new series tests, alternating series, power, p-series, geometric series, any of the ones that we've seen before. So each one of these problems is long, which is why there's only 4 in the activity. The project is 5 of these. Okay, I will walk around if I can help.